In this video, we will talk about our project, which entitled as Multi-Robot Warehouse Optimization. Here, we have explored that how intelligent coordination between multiple robots can transform efficiency, reduce energy consumption, and maximize performance in modern warehouse. So before going into the depth, let's consider a scenario. Just imagine that there is a warehouse where multiple robots can think, they can plan and optimize every move. So with that said, we welcome you all to the future of logistics. In the second slide, it contains information about group member. Here we have Soban Chakma, Gulshan Kumar Nath, Rahul Ray, and myself. And together, we as a team, we have focused on energy efficiency and system performance. And our team brings strategy, planning, and performance together into one unified system. Let's go to the slides third. So let's discuss about the robotic system. So scaling robotic system is not as simple as adding more robots, because in the modern warehouse, uh, it may have multiple challenges. Here we have faced three major challenges. First one is battery life. So robots, as we all know that robots have limited energy, and without smart charging strategies, unexpected shutdowns can disrupt operation. Second major challenge is load dynamics. So heavier loads consume more energy, and it causes to reduce efficiency and operational range. Third challenge is task control, as the poor task allocation may lead to idle robots or overloaded ones, and it may lead to that both hurting productivity. These challenges demand smarter coordination and decision making. Let's come to the slides 4. Here we will talk about one of the biggest obstacle, that is energy efficiency. So here in this slide we are highlighting inefficiencies, unnecessary movements, and charging delay. So one of the biggest obstacle, that is poor assignment. Let's consider that in any task, we have assigned robots without considering their initial position, and this kind of assignment may lead to the wastage of time and effort. And another obstacle, that is energy wastage. That is, if we have redundant movements, then this may increase overall energy consumption. And next is the battery failure. So lack of predictive charging may causes robot to fail mid task, and there may often happen that movement issue may also arises, because unnecessary travel reduces throughput and slow operation. So traditional system ignore real world constraint, and that's where optimization become critical. Let's come back to the uh, next slide. So here we will discuss about the strategic objective. Uh, our approach is to focus on three major objectives. First one is to minimizing energy usage. So our team has aimed to reduce energy consumption while ensuring that there must be 100% task completion. Second objective is to reduce total movements. So optimizing robot path may lead to the minimization of unnecessary travel and wear. And the third major objective, that is optimizing the total charging cycles. So as we know that smart charging may uh, may lead to the creation of strategies that maximize availability and reduce downtime. Let me call my next group member, that is Sovan Chakma, to proceed further.
Thank you, Vaibhav. Now I'll walk you guys through how our system is designed at a very high level. So first of all, we model the warehouse as a 2D grid environment where everything happens, the robot movement, the item pickup, and the delivery. On top of this, we define specialized agent roles, meaning each robot is not just moving randomly, but is assigned tasks intelligently. And finally, we integrate everything using structured data through JSON, which allows us to simulate the entire warehouse in a reproducible and scalable way. So overall, you think of it is three layers. First one, the grid is the physical space. Second, the agents are the decision makers, and the third are the data integration connects everything together. Coming to the slide number 7. Now let's understand how each robo is modeled. So each robo operates based on five key parameters. The position, first position, which tells us where the robot is in the grid at any moment. So the second, the physical capacity, which defines how much weight it can carry. This is important because we cannot overload a robot. The third, battery health, which tracks how much energy the robot has left during execution. Fourth, base weight, which is the weight of the robot itself. And finally, the current load, which is the weight of items it is carrying. So the key idea here is that robot decisions are not static. They depend on these dynamic parameters. So every moment and every task assignment depends on where the robot is, how much it is carrying, and how much energy it has. Um, Now, this brings us to the most important part, our energy model. Unlike simple systems, we don't assume fixed energy uses. Instead, we use a load aware model where energy depends on how heavy the robot is at any moment. So energy is like the formula given here is slightly wrong, but I would include distance uh, with base and weight load contributed in the energy. This means that if the robot carries more load, it consumes more energy. If it carries less, energy consumed is lower. So the system behaves more like the real world because this because of this, heavy task becomes more expensive. Robots must be chosen carefully, and energy efficient becomes part of the planning itself. This is what makes our system energy aware, not just energy aware, not just task aware. So coming to slide 9. um, Now once a robot is assigned a task, it needs to move efficiently. For that, we have BFS, which is breadth first search. Here is how it works in our system. First, we initiate the search from the robot's current position. Then we expand, meaning we explore all possible directions up, down, left, and right. We validate to ensure the robot stays within the warehouse boundaries. Then we identify the target, either an item or a charging station. And finally, we optimize because BFS guarantees the shortest path in an unweighted grid. So the key takeaway is BFS ensures minimum steps which directly reduces energy usage. Coming to the next slide. Now comes the core decision making part. This is task allocation. Now we implemented two strategies here to compare the performance. The first one is simple assignment and second one the smart assignment. The goal here is to understand how better decision making can improve efficiency. Up to now, we have seen how robots are modeled, how energy is calculated, and how paths are planned. Now the question is, which robot should do which task? That's where our assignment strategies come in. In simple assignment, tasks are given in a round robin manner. Robots don't consider distance or load. This leads to inefficiency and imbalance. But in smart assignment, we use a heuristic-based approach. Each robot is evaluated before assigning a task. We consider both distance and the load. So instead of blindly assigning any task, we choose the best possible robot for each task. So, in a summary, our system combines realistic robot modeling, energy aware decision making, efficient part planning, and intelligent task allocation. This creates a much more optimized and realistic warehouse. Now I will hand over to the next speaker, Wilson Kumanat. That's all for my side.
Thank you so much, Chakma, for the explanation. Now I will explain the next part of our project. So now let's first understand why a simple approach fails in a real warehouse system. In a basic round robin assignment, items are assigned sequentially to robots without considering any intelligence. So this leads to the three major problems that are specified in the slide. So in the first box, there comes the distance blindness, which means the system ignores how far a robot is from the task. Uh, Means robot might travel a long distance even when the closer robot is available to the item. So this is the problem related to distance. And next, coming to the charging loop, when a robot is overloaded, it consumes more energy and needs to charge frequently. This creates unnecessary interruption and reduces efficiency. So this is also a problem. And in the third box, we have like overload trapping. Means robot ends up doing most of the works while other remains underutilized. Means specifically, we are assigning most of the tasks to single robot. This imbalance is increasing. This imbalance increases the energy consumption and reduces overall system performance. So clearly, a simple assignment strategy is not suitable for efficient multi-robot system. So in the next slide, mm, we have overcome that issues and we have introduced a smart assignment strategy to our problem. So instead of assigning tasks randomly, we use a heuristic-based approach to consider multiple factors in our paradigm. So the diagram, the system calculates a cost for each robot item pair and select the robot with the minimum cost. Uh, in the second, it means it maintains a dynamic awareness and it evaluates the robot current position and workload before making a decision. And then a capacity check, like this ensures that the robot can actually carry the item before assigning it. Overall, this process leads to a balanced workload distribution and efficient task execution. So next, in the next slide, and like we have the cost logic, how we are performing the cost based on the robot and
भैया
item.
थोड़ा सा साउंड कम आना
Uh,
है.
so now let's understand the core idea behind the assignment, the item assignments to the robot,
थोड़ा
which
सा
is
साउंड
basically
कम
a cost
लीजिएगा.
function we have included in our project. So the cost is calculated using the main two components like distance and the load. In the left side, we have like the distance represent how far the robot is from the item's destination. This ensures we prefer robots that are closer to the task. And in the right side, we have the load penalty. It's calculated based on how many items are already assigned to the robot, and we are multiplying the length of each item that is being assigned to the robot by 5. Uh, like if you have a large grid and large items, then it may leads to that it not perform well as compared to the simple strategy. So we are multiplying 5 to that. This prevents any single robot from becoming overloaded. So the final cost is like distance and load penalty. We have included in our heuristic like distance and load penalty, both those things to our cost. So this balances the task are distributed. This balances the task that which are distributed to the robots efficiently in a creative and without creating the bottlenecks. It is efficiently distributed to all the robots. So in the next slide, we have like predictive charging. This is the another important feature of our system And instead of reacting after the battery is drained, we make a decision in advance. So in the step one that we before making the decision, we are performing the battery audit. Like the system calculates how much energy is required for the next movement by taking the next item. So in the step two, in the next step, like step two, there is a safety check. We compare required energy with the current battery level. In the next step, if the battery is insufficient, we'll check the battery level. If the battery is insufficient, then the system takes intervention and the robot goes to the nearest charging station. The next step after coming to the next charging station, it becomes full charge after we have to wait for some time, and if it can balance other robots also. But the main objective is like the the resumption is like that it is assign the task automatically to every robots based on this approach. So next, like it will prevent the robots getting stuck midway and ensure a smooth execution for overall representation. So next is state space. Like we have different stages of state space. So we have a state of robot, like what is the robot position and what is the battery level, like what is the robot's battery level and current load, delivered item, number of delivered items that the robot delivered. In the second, like perform peak and movement operations transitioning between the states. In the third, at each step, battery management is applied if needed, charging it triggered before continuing. So at final, robot delivers the item and repeats the cycle for the next task. So the overall system behaves like state-driven decision process, ensuring the efficiency at every step. So I've explained my part, and I would like to invite Rahul Roy for the next explanation of our project, like how the code works and how the output comes, like how the dependency between the functions. Then he will decide. He has decided that part, and he will explain the whole thing. So Rahul, you can continue with your part.
Okay, thank you, Gulshan, for your explanation. Uh, so now I will explain how the code works, and I will compare the two assignment system, the smart assignment and our the normal simple one. So if you see the code, so first we define a class for our warehouse system. So the warehouse is defined as a graph with nodes m and edges n. So then the system, then we define the item class which have weights, then destination, then is it picked or is it delivered, and then we define the class for the robots. So the robot specification are its current position, its capacity, then its battery, and then its how much it have current battery percentage, then its load. Then we define the energy function. The energy function is defined as alpha into weight plus load. So for part planning, we have used BFS as our main algorithm, which used to compute the shortest path between the position in a grid. So then this is for distance calculation. Then these are the two assignment algorithm for our project. So first we have the smart assignment system. So in smart assignment system, we assign each item to the robot that minimizes a cost function based on the distance and the current load. So this help in reducing travel distance and balancing workload. So our second is the simple assignment, where each item are assigned to the robot in a round robin format. So then this is the main function which assign item to robots, allows them to pick items based on the capacity, and it moves them step by step along the BFS path. So then before moving, each robot checks whether it has enough battery to reach the destination or not. If not, it first go to the nearest charging station and recharges. Uh, then this is the movement part. So during movement, energy is consumed, and once the robot reaches the destination, it delivers the item. So the finally the program computes total energy, total moves, and total charges for both the states. So now moving to the result. So now I will show how the output looks. So this is our overall code, and this is the output. So you can see in the smart assignment strategy, so this is the graph plane, and at last the total energy used is 94 units, total number of moves is 10, and the total number of charges is 1. Similarly, for the simple assignment, this is the graph plane, and the total energy used is 134 units, the total number of moves is 14, and the total number of charges used is twice. So now moving to the result. So now moving to the results, I will compare both the strategies using total energy, total moves, charging events, and load distribution. So the simple strategy consumes 134 units of energy, while the smart one reduces it to 94 units, giving about a 30% improvements. Secondly, the total number of moves decreases from 14 to 10, making the system around 28% faster. Thirdly, the charging events reduces from 2 to 1, which cuts the charging downtime by about 50%. Also, the simple strategy shows imbalance load distribution, whereas the smart one distributes tasks more evenly across robots. So now analyzing these results, the improvement mainly comes from the heuristic-based assignment used in the smart one. First, it reduces unnecessary movements by assigning tasks to the closer robots. Second, it balances the load, preventing overload on a single robot. Thirdly, it reduces charging frequency, which improves overall system efficiency. Finally, some future improvements. So we can use A-star algorithm with obstacle handling for more realistic navigation. So we can also build a real-world dashboard to monitor robot states. So additionally, machine learning techniques can be applied to further optimize task allocation. So in conclusion, the smart assignment strategy significantly outperforms the simple round-robin approach in terms of energy efficiency, speed, and the overall system performance. So this is our overall project. So